following presentation was produced by the Clemson University Cooperative Extension Service through funding by the Southern Regional Aquaculture Center, United States Department of Agriculture, and the U.S. Fish and Wildlife Service, United States Department of the Interior. A good supply of high-quality water is perhaps the most important asset of a successful fish producer. All other things being equal, a pond with good water quality will produce more fish than a pond with poor water quality. Poor water quality could mean reduced growth or a complete loss of fish. And since the type of water source directly influences the quality of water in a pond, it is important to select one which results in optimum productivity or use corrective measures for those ponds with existing water sources which produce less than satisfactory water. The purpose of this tape is to show the types of water sources available to pond owners, how these water sources differ in quality with respect to type and location, and to describe the basic ionic constituents present in each source. A discussion on dissolved gases, plankton, aquatic plants, turbidity, and pollutants is also included. Testing procedures for several basic water quality parameters will be presented and possible corrective measures will be discussed. In addition, special considerations regarding flow-through systems will also be included. Ionic composition of water sources. Water contains many elements and compounds which are dissolved in it. Collectively, the dissolved mineral forms are called ions. For example, limestone or calcium carbonate, when dissolved in water, results in the formation of calcium and carbonate ions. The absence or presence of various ions determines the quality of water in a pond. The basic composition of compounds in water is determined by the location of its source. For example, well water obtains ions directly from mineral deposits of the aquifer in which it is located. Therefore, water from a limestone aquifer will contain large quantities of calcium and carbonate ions. Surface water will contain ions dissolved from the stream bed and from runoff over land into the stream. In many areas, various types of water may be obtained by drilling at different depths. 3 types of fresh groundwater sources are usually present in the south. Water from a limestone aquifer will contain mainly calcium and carbonate ions. Other ions are present, but exist in relatively smaller quantities. Water derived from this aquifer will have high concentrations of calcium and carbonate ions. Another groundwater source is from a well drilled into a formation of sodium bicarbonate. The predominant ions in this source are sodium and bicarbonate with smaller quantities of carbonate ions. These sources are commonly called soda wells and are usually located at a greater depth than limestone aquifers. The third type generally comes from strata which have very few available ions, mainly from strata deeper than sandy type aquifers, and few ions are present in these wells. By observing aquifer maps such as this, a producer may determine what type of groundwater source is located in his or her area. For example, a farmer at location A could drill a well and expect water from a limestone aquifer. On the other hand, any well drilled at location B would only produce water high in sodium and bicarbonate since the limestone aquifer is absent in this area. Maps similar to this one for your area may be obtained through your local Soil Conservation Service office or State Water Resources Agency. Many producers have access to surface water. In some cases, a surface water source will be of sufficient quality and quantity to warrant its usage. However, in most cases, several characteristics of surface waters may make them less desirable as sources for fish production ponds. Many streams are intermittent, that is, their flow is not constant. For example, during periods of low rainfall, the stream may slow or even dry up. On the other hand, excess precipitation may produce flooding, which could rise above dams and cause the escape of fish or the introduction of wild fish. Since the water quality of the stream is determined by the geology of its drainage basin or emerging springs from underground, quality varies considerably from stream to stream. For example, streams located in agricultural areas may receive drainage from fields which are treated with insecticides and herbicides. Streams receiving water from areas where livestock are held may contain high levels of organic materials such as manure, which may adversely affect water quality. However, well-managed drainage basins may add beneficial ions to the water such as calcium and carbonate. Another problem which often arises when surface water is utilized is the introduction of wild fish into the pond. For example, sunfish may reduce production considerably since they compete with and eat other fish species. Other species may actively compete with the desired species for food or reduce water quality by stirring up the pond bottom. To reduce the input of wild fish, excluders such as this must be placed at the inflow to the pond. Installation of drain pipes such as this will prevent fish from swimming into the pond from drainage ditches. Due to the various problems associated with most surface waters, it is wise to use groundwater whenever possible. However, there are exceptions. For example, in some areas where spring-fed streams are common, it may be more economical to use this source instead of drilling a well. Another option for using surface water, particularly appealing for sport fish ponds, is watershed ponds. These ponds are built in areas that collect rainwater from the immediate drainage basin. There are usually no wild fish problems in these types of ponds. However, the iron concentration of water is usually very low. Salinity. In some coastal areas and in areas that have underground salt domes, the high salinity of water sources may prevent production of freshwater fish. The term salinity refers to the total concentration of all dissolved ions in water. If you are unsure about the salinity of your water source, contact your county extension agent. pH, total alkalinity, and total hardness. The ionic composition of water is so important because it affects a number of water quality factors. 3 of these parameters, pH, total alkalinity, and total hardness, will now be discussed. pH. The pH is a measure of the hydrogen ion concentration and indicates if the water is acidic or alkaline. Since pH represents the negative log of the hydrogen ion concentration, the lower the pH, the greater the number of hydrogen ions in the water, while higher pH indicates lower numbers of hydrogen ions. The pH scale ranges from 0 to 14, with 7 being neutral. Waters with pH values below 7 are termed acidic. Those with values above 7 are said to be basic. The greater the departure from pH 7, the more acidic or basic the water is. The pH of a pond is directly influenced by the concentration of carbon dioxide in the water. Carbon dioxide is taken up by phytoplankton during the day as photosynthesis occurs. Since carbon dioxide is an acidic substance, pH rises when it is removed. As photosynthesis ceases during the night, carbon dioxide is returned to the water by phytoplankton respiration, and pH falls. The degree of fluctuation in pH is directly influenced by the buffering capacity of the water, which is its resistance to changes in pH. The buffering capacity is in turn determined primarily by total alkalinity and to a certain extent total hardness levels of the pond, which will be discussed shortly. Fish are sensitive to extreme values of pH. The acidic and alkaline death points for most fish are approximately pH 4 and 11, respectively. However, slow growth may occur in moderately acidic and alkaline waters. In waters which are not buffered sufficiently, the pH may remain at these values for long periods of time, thereby inhibiting growth. In properly buffered ponds, the pH will remain between approximately 6 and 9 most of the time. This range is desirable for fish production. The pH in a pond directly affects algae growth, which influences oxygen concentration in fish health. The pH also affects the toxicity of a number of naturally occurring compounds such as ammonia and hydrogen sulfide and chemicals which are added to the pond for management purposes such as copper sulfate. Total alkalinity and total hardness. Earlier it was mentioned that the daily degree of fluctuation in pH is a function of the buffering capacity of the water. The greater the buffering capacity, the less the fluctuation in pH. The principal factors which influence this buffering capacity are total alkalinity and total hardness. Total alkalinity refers to the total concentration of bases in water expressed as calcium carbonate. Another way to think of total alkalinity is resistance to changes in pH. Waters with high total alkalinity will resist changes in pH more than waters with low total alkalinity. For example, in the procedure used to test water for total alkalinity, sulfuric acid is added to the water sample until the available bases have been titrated, that is, taken up by the acid. The greater the number of bases, such as carbonate and bicarbonate ions, the greater the total alkalinity. Total hardness refers to the total concentration of divalent metal ions expressed as calcium carbonate. In most waters, calcium and magnesium are the principal ions which make up total hardness. Alkalinity and hardness may be measured through the use of test kits such as this one. Kits such as this are relatively inexpensive and include supplies for testing other water quality parameters which will be discussed in subsequent tapes of this series. Kits may be purchased from scientific supply companies. As mentioned earlier, the alkalinity test measures the amount of standard sulfuric acid required to lower the pH to a specific level. Thus, the number of drops of acid required to reduce the pH to a specific level represents the amount of resistance to pH change of the water, which in turn is a measure of the buffering capacity or total alkalinity. Included in most test kits are a high and a low range test for alkalinity. Initial testing of alkalinity should start with the high range method. To use the high range test, proceed as follows. First, obtain a sample of water to be tested. Water should be collected away from the pond bank if possible to ensure that stirred up mud will not influence the test. Water should also be collected using a clean container. It is very important to use clean containers to collect water samples, since residues in the jar or bottle may influence measurements. Once samples have been collected, rinse a plastic measuring tube provided in the kit with water to be tested. Pour the contents of this tube into the mixing bottle. Then add 1 or 2 drops of phenolphthalein indicator solution to the sample and swirl to mix. An indicator adds color to a solution to be tested. That is, after addition of an indicator, the water usually changes color when it reaches a certain pH. Then if a solution termed the titrant is added, the water eventually changes color again. This is termed the endpoint. By knowing the amount of titrant added to reach the color change at the endpoint, the concentration of the tested substance may be calculated. If the water remains colorless after the addition of the phenolphthalein indicator solution, the phenolphthalein alkalinity is 0. However, if the water becomes pink, add sulfuric acid solution using the dropper drop by drop to the sample, swirling after each drop. The solution will turn pink only if the pH of water is above 8.3. Phenolphthalein measures resistance to pH changes above 8.3. Count each drop as you add it. The dropper should be held vertically while dispensing drops. Add the sulfuric acid until the sample becomes colorless and record the number of drops dispensed. Remember, if the sample did not turn pink after the addition of phenolphthalein indicator, no sulfuric acid should be added. In this case, the drops of sulfuric acid used to this point is 0. Now add 1 bromocresol green methyl red powder pillow to the sample and swirl to mix. The sample should take on a blue-green color. Then add sulfuric acid as shown previously to change the color from blue-green to pink. This happens at pH 4.5. Record the number of drops used. Then add the total number of drops of sulfuric acid used. For example, if you use 2 drops of sulfuric acid to change the sample color from pink to colorless after adding phenolphthalein indicator, and 5 drops to change the color from blue-green to pink after the addition of the powder pillow, the total number of drops used is 7. The total alkalinity of the sample may now be obtained by multiplying the number of drops of sulfuric acid used by 17.1. The result is the total alkalinity as milligrams per liter calcium carbonate. Since total alkalinity is usually what you are interested in, you can neglect the addition of phenolphthalein and simply add bromocresol green and titrate to pH 4.5. If the results of the high-range test show a fairly low alkalinity, for example 1 or 2 drops or 17 to 34 milligrams per liter calcium carbonate, the low-range test should be used for greater accuracy. The low-range test is identical to the high-range test, except in this case the sample size is increased, thereby resulting in greater sensitivity due to the lower concentration of indicator which is present. In other words, the indicators that are added in the low-range test are diluted more than they are in the high-range test. The greater sensitivity in the low-range test results because more drops of sulfuric acid must be added to the same water sample in the low-range test than in the high-range test. To measure the total alkalinity using the low-range test, proceed as follows. First, fill the mixing bottle to the 15 milliliter mark. Proceed as in the high-range test. Add phenolphthalein indicator solution and sulfuric acid solution if necessary. Then add a bromocresol green methyl red powder pillow, and then sulfuric acid until the endpoint or color change is reached. To calculate the total alkalinity, multiply the total number of drops of sulfuric acid used by 17.1. Divide this number by 2.5. The result is the total alkalinity as milligrams per liter or parts per million calcium carbonate. Division by 2.5 takes a larger sample size into account. It should be mentioned that total alkalinity is composed of three types of alkalinity: hydroxide, carbonate, and bicarbonate alkalinity. Relationships between these types of alkalinity are normally included in test kits, and many prove confusing. However, what fish farmers are interested in is total alkalinity, which may be measured as described. Total hardness is measured using a test kit as well. To measure total hardness, proceed as follows. First, obtain a water sample from the pond in the same manner as the alkalinity test. Remember, use a clean sampling jar or bottle. Rinse a plastic measuring tube provided with the kit with the water to be tested, then fill and pour the contents into the mixing bottle. Now, add 3 drops of buffer solution to the mixing bottle and swirl to mix. Then, add 1 or 2 drops of hardness indicator solution to the mixing bottle and swirl to mix. The sample should turn pink or orange. Add titrant reagent drop by drop while swirling until the color changes from pink to blue. Remember to hold the dropper directly above the sample, taking care not to touch the dropper to the side of the mixing bottle. To calculate the total hardness, multiply the number of drops of titrant used by 17.1. The result is the total hardness as milligrams per liter calcium carbonate. Levels of total alkalinity and total hardness desirable for fish culture generally fall within the range of 75 to 300 milligrams per liter. Generally, productive waters have total hardness and total alkalinity values of approximately the same magnitude. Waters with total alkalinities less than 15 to 20 milligrams per liter, for example watershed ponds, surface water, or non-ionic well water, usually cause reduced algae growth due to the lack of available carbon required for photosynthesis, and also cause large changes in pH. Waters with low total alkalinity are also not buffered against pH change, and pH values may fluctuate greatly during a 24-hour period. For example, one can see that fluctuations in pH are greater in the pond with low alkalinity as compared to the pond with moderate total alkalinity. If the total alkalinity is fairly high, for example greater than 75 milligrams per liter, and the total hardness is low, the afternoon pH may rise to 10 or above and remain for several hours. In this situation, the lack of appreciable hardness may result in surplus bases such as carbonate, which in turn increases pH. Also, the lack of calcium associated with low hardness usually results in reduced growth of fish. Therefore, again, the best water source for fish culture contains total alkalinity and total hardness levels of the same magnitude and 75 to 300 milligrams per liter each. This type of water is commonly produced by limestone aquifers. Unfortunately, some producers will not have access to a limestone aquifer as their water source. The following is a summation of the typical deficiencies of other common water sources in this area. Soda wells typically produce waters with alkalinity levels of 75 to 250 milligrams per liter and hardness levels of 0 to 5 milligrams per liter. As mentioned, pH values will be high in the afternoon in waters of this type. Problems associated with low hardness, as discussed earlier, may also occur. To reduce afternoon pH, hardness must be increased in this type of water. A common method is the application of agricultural gypsum, which is calcium sulfate. To find the amount of gypsum needed to treat your pond, refer to your county extension agent or aquaculture specialist. If the pond has not yet been filled, the gypsum may be broadcasted over the bottom of the dry pond. Subsequent disking will ensure even distribution and allow the gypsum to react with the pond mud once filled. However, most applications will be in ponds which are full. In this case, gypsum may be placed on a plywood platform on a boat. While navigating the boat throughout the pond, gypsum is evenly distributed. Some water sources, such as surface water or some ionic wells, produce water in which total alkalinity and total hardness levels are exceedingly low. As mentioned, waters with alkalinities below 15 to 20 milligrams per liter will not produce sufficient growth of algae. Also, ponds with alkalinities below 20 milligrams per liter will not respond to fertilization as well as waters of higher alkalinity. Furthermore, due to the combined effects of low total alkalinity and hardness, pH may be low for extended periods of time. In order to correct this situation of low total alkalinity and total hardness, liming is performed. The decision to lime should be based on total alkalinity and total hardness measurements of the pond water in question, since water quality varies from site to site. If both total alkalinity and total hardness are above 30 milligrams per liter, no lime is needed. If total alkalinity and total hardness are below 20 milligrams per liter, liming is necessary, and soil samples from the pond bottom should be taken and sent to your county extension agent to determine the liming requirement. Soil samples can easily be obtained by using a boat while scooping samples from the bottom at different locations. Most land-grant universities can perform the test for free or at a small charge. If lime is needed, the selection of a liming agent is then made. Hydrated lime and burnt lime have been used as liming agents, but their use is discouraged since applications often cause extremely high pH. Agricultural limestone, on the other hand, does not cause excessively high pH when applied properly, and therefore is the best liming agent. It is also less expensive than other liming agents. The best agricultural limestone is of fine particle size and high neutralizing value. For example, a limestone with a 90% neutralizing value is 90% as effective as pure limestone. By applying the neutralizing value of your limestone with data received from your county extension agent, the required level of lime is obtained. Application of lime should occur in the fall or winter since fertilization normally occurs in the spring. This delay allows the lime time to react with the pond bottom, which increases the total alkalinity and hardness and increases the effectiveness of fertilizer applications, if any. As with the application of gypsum, lime may be broadcast directly on the bottom of a dried pond or may be distributed evenly throughout the pond by boat. It is important to get an even, thorough coverage of pond bottom. This buffers all of the mud. Dissolved gases. Generally, 3 dissolved gases are of importance in water sources used by pond owners. These are dissolved oxygen, carbon dioxide, and hydrogen sulfide. Dissolved oxygen. Maintaining adequate concentrations of dissolved oxygen is critical to successful fish production. Adequate dissolved oxygen is necessary not only to prevent massive fish kills, but also to maintain healthy and growing fish. Generally, it is desirable to maintain dissolved oxygen levels above 5 milligrams per liter. Dissolved oxygen concentrations from 1 to 5 milligrams per liter usually cause reduced growth after prolonged exposure. Values below 1 milligram per liter prove lethal to most fish if exposure is prolonged. Although the atmosphere is 21% oxygen by volume, this oxygen is not available directly to fish unless it is dissolved into the water. Even though oxygen will diffuse into the water, the rate of mixing it into the water is slow. Therefore, dissolved oxygen concentrations of a pond are mainly dependent on the oxygen production resulting from photosynthesis by phytoplankton and mixing of oxygen at the surface down into the water. Losses of oxygen from a body of water are primarily from respiration of phytoplankton, muds, and bacteria by which oxygen is taken up. Other organisms present in the pond, including fish, also take up oxygen, but to a smaller extent than phytoplankton. A summary of approximate gains and losses of dissolved oxygen in a typical pond is shown here. The importance of phytoplankton's role in both gains and losses is easily seen. The processes of photosynthesis and respiration by phytoplankton alternate between night and day. That is, photosynthesis requires sunlight and only occurs during the day. At night, photosynthesis ceases and respiration is the dominant process. This results in fluctuations of pond oxygen levels from day to night. As this graph shows, oxygen reaches its lowest level shortly before dawn due to respiration throughout the night. As sunlight reaches the phytoplankton, photosynthesis occurs and causes oxygen levels to peak shortly before dark. In ponds with heavy plankton blooms, a die-off may occur which will cause a sudden depletion of dissolved oxygen. As shown in the graph, dissolved oxygen concentrations suddenly dropped immediately after the die-off of plankton and remain low for several days. Die-offs such as this occur mainly during hot, calm weather in ponds with heavy blooms. In this situation, a large fish kill can be expected unless corrective measures are immediately undertaken. Cloudy weather will also result in decreased dissolved oxygen concentrations due to reduced photosynthesis by phytoplankton. As shown in the graph, as cloudy weather persists for several days, dissolved oxygen concentrations decrease. Extremely windy weather or heavy rains may cause turnover or mixing of a pond, resulting in mixing of deoxygenated bottom waters with those throughout the pond, which may also cause reduced oxygen content. Measurements of dissolved oxygen may be made with a portable oxygen meter or with a kit. The kit method is more time-consuming, but it is less expensive. For a description of testing methods and corrective measures regarding dissolved oxygen, see videotapes 2 and 3 in this series. To correct low oxygen levels, a variety of aeration devices are available. Each aerator is different in price and performance. To select the one best suited for your needs, contact your county extension agent. Carbon dioxide. Although carbon dioxide diffuses much more rapidly from air to water and vice versa than does oxygen, water levels of this gas are usually low due to its small atmospheric concentration. However, in some cases, dissolved carbon dioxide concentrations may increase considerably. The most common sources of high carbon dioxide are some types of well water, ponds after a plankton die-off, or water in ponds covered by ice. If well water high in carbon dioxide is pumped directly into the pond, carbon dioxide levels may increase. Ideally, a spray valve or other device should be placed on the wellhead to allow water to spray and lose carbon dioxide. Fish can tolerate relatively high concentration of carbon dioxide, but tolerance is reduced in the presence of low oxygen. Also, during periods of high carbon dioxide, the pH is usually low. Unfortunately, carbon dioxide concentrations are usually high when oxygen is low. For example, at night, carbon dioxide levels are greatest due to production of carbon dioxide by phytoplankton respiration. At the same time, oxygen levels are low due to respiration as well. However, maintaining adequate oxygen levels usually prevents carbon dioxide toxicity in this case. It is wise to initially test your water source for carbon dioxide levels. Carbon dioxide can be reduced by application of hydrated lime. However, care should be taken not to raise pH too high, causing fish kills. Testing procedures and corrective measures regarding carbon dioxide will be discussed in videotape 3 of this series. Hydrogen sulfide. Hydrogen sulfide may be present in some water sources. Although highly toxic to fish, this gas is rarely a problem in freshwater pond culture. However, toxicity of hydrogen sulfide increases as pH decreases. Therefore, in ponds which have acidic waters and well supplies with increased hydrogen sulfide, problems occur. Hydrogen sulfide is also more of a problem in saltwater ponds. Liming to increase pH in this case will usually solve this problem by increasing the buffering capacity of the water, thereby stabilizing pH. Hydrogen sulfide has a distinctive rotten egg smell and may be easily detected in this manner. For further testing, consult your county extension agent. Plankton. The establishment of a planktonic community is essential to successful fish production. Plankton, which consists of microscopic plants and animals, provides a food base for the pond, regulates many water quality parameters such as oxygen and pH, and prevents the growth of large aquatic plants. To establish a planktonic community, fertilization is normally required after total alkalinity and hardness are brought into suitable ranges. Fertilizer may be distributed on a platform in the pond, such as this. In fed ponds, fertilization may be unnecessary because of nutrients produced by feeding. A rule of thumb on desirable bloom levels in ponds is to fertilize when a white object can be seen through the water at a 30-inch depth. If the object cannot be seen at a 30-inch depth, no fertilization is needed. If you have questions regarding fertilization, contact your county extension agent. Aquatic plants. Aquatic plants may become problems in some ponds. Large areas of the pond may be covered by dense growths of a variety of these plants, which may restrict harvesting, fishing, and deplete nutrients from the pond. As mentioned, plankton will reduce growth of aquatic plants. This is due to the shading effect of plankton, which prevents adequate amounts of light to reach the bottom. Shallow edges and standing timber will increase aquatic weed growth. The edges may have to be deepened and strips of vegetation removed to alleviate problems. In some cases, however, chemical control or weed-eating fish may be used. Consult your county extension agent for more information on the use of chemicals in weed-eating fish such as tilapia and grass carp. Turbidity. Turbid water contains suspended materials which interfere with the passage of light. As mentioned, plankton interferes with light passage, and this is desirable. However, turbidity resulting from clay or other substances is not desirable, as it restricts the growth of plankton. To control turbidity due to clay or organic substances, contact your county extension agent. To alleviate turbidity problems, the watershed may have to be stabilized, livestock and bottom-disturbing fish such as bullheads or mudcats removed, or compounds such as alum may have to be added. Pollutants. As mentioned earlier, some water sources may contain pollutants such as pesticides, heavy metals, and other substances. Unfortunately, the best way to detect if pollutants exist in your water is the presence of dead fish. If fish kills occur for unexplained reasons, consult your county extension agent immediately. You will have to know what potential compounds may be in the water supply to have testing done. Considerations for flow-through systems. Water quality in flow-through systems such as holding troughs is dependent on the quality of the source. Minimum total alkalinity and total hardness are usually adequate since most producers do not hold fish for extended periods of time. Sufficient oxygen may be maintained through the use of air blowers or bottled oxygen. By spraying incoming water through valves, carbon dioxide is liberated and additional aeration is achieved. Problems with hydrogen sulfide and other compounds such as iron may be removed by aeration. However, more sophisticated measures may have to be taken in some cases. Remember, the key to successful fish production is good water quality. Hopefully this tape will enable you to choose a quality water source or manage an existing one. Also, remember to contact your county extension agent or aquaculture specialist when problems occur. The following presentation was produced by the Clemson University Cooperative Extension Service through funding by the Southern Regional Aquaculture Center, United States Department of Agriculture, and the U.S. Fish and Wildlife Service, United States Department of the Interior. A good supply of high-quality water is perhaps the most important asset of a successful fish producer. All other things being equal, a pond with good water quality will produce more fish than a pond with poor water quality. Poor water quality could mean reduced growth or a complete loss of fish. And since the type of water source directly influences the quality of water in a pond, it is important to select one which results in optimum productivity or use corrective measures for those ponds with existing water sources which produce less than satisfactory water. The purpose flow or even dry up. On the other hand, excess precipitation may produce flooding, which could rise above dams and cause the escape of fish or the introduction of wild fish. Since the water quality of the stream is determined by the geology of its drainage basin or emerging springs from underground, quality varies considerably from stream to stream. For example, streams located in agricultural areas may receive drainage from fields which are treated with insecticides and herbicides. Streams receiving water from areas where livestock are held may contain high levels of organic materials such as manure, which may adversely affect water quality. However, well-managed drainage basins may add beneficial ions to the water, such as calcium and carbonate. Another problem which often arises when surface water is utilized is the introduction of wild fish into the pond. For example, sunfish may reduce production considerably since they compete with and eat other fish species. Other species may actively compete with the desired species for food or reduce water quality by stirring up the which have very few available ions, mainly from strata deeper than sandy-type aquifers, and few ions are present in these wells. By observing aquifer maps such as this, a producer may determine what type of groundwater source is located in his or her area. For example, a farmer at location A could drill a well and expect water from a limestone aquifer. On the other hand, any well drilled at location B would only produce water high in sodium and bicarbonate since the limestone aquifer is absent in this area. Maps similar to this one for your area may be obtained through your local Soil Conservation Service office or State Water Resources Agency. Many producers have access to surface water. In some cases, a surface water source will be of sufficient quality and quantity to warrant its usage. However, in most cases, several characteristics of surface waters may make them less desirable as sources for fish production ponds. Many streams are intermittent, that is, their flow is not constant. For example, during periods of low rainfall, the stream may. This tape is to show the types of water sources available to pond owners, how these water sources differ in quality with respect to type and location, and to describe the basic ionic constituents present in each source. A discussion on dissolved gases, plankton, aquatic plants, turbidity, and pollutants is also included. Testing procedures for several basic water quality parameters will be presented and possible corrective measures will be discussed. In addition, special considerations regarding flow-through systems will also be included. Ionic composition of water sources. Water contains many elements and compounds which are dissolved in it. Collectively, the dissolved mineral forms are called ions. For example, limestone or calcium carbonate, when dissolved in water, results in the formation of calcium and carbonate ions. The absence or presence of various ions determines the quality of water in a pond. The basic composition of compounds in water is determined by the location of its source. For example, well water obtains ions directly from mineral deposits of the aquifer in which it is located. Therefore, water from a limestone aquifer will contain large quantities of calcium and carbonate ions. Surface water will contain ions dissolved from the stream bed and from runoff over land into the stream. In many areas, various types of water may be obtained by drilling at different depths. 3 types of fresh groundwater sources are usually present in the South. Water from a limestone aquifer will contain mainly calcium and carbonate ions. Other ions are present, but exist in relatively smaller quantities. Water derived from this aquifer will have high concentrations of calcium and carbonate ions. Another groundwater source is from a well drilled into a formation of sodium bicarbonate. The predominant ions in this source are sodium and bicarbonate with smaller quantities of carbonate ions. These sources are commonly called soda wells and are usually located at a greater depth than limestone aquifers. The third type generally comes from strata